quasi-inflection point. That is, at the inflection point, there is a slope. Then you can last for more than a few e-folds. So you can keep on being in quantum diffusion in, say, in phase space, full phase space, not in the slow roll approximation. And therefore, one could have a significant enhancement of the diffusion at that point. Have you explored that?
Yeah, so, well, we've only really studied simple models with the ultra slow roll so far. So we were really studying these plateau, plateau regions, well, plus then the Starobinsky with the linear potential. As you say, to get an extended ultra slow roll, you can indeed have if the potential has the correct shape, it can be an extended region. And we've only looked at cases where you would have a transient ultra slow roll. So I think that's right. So I think we would, yeah, so I couldn't say necessarily how things change there. To some extent, indeed, when we see this simple behavior of the poles here, these additional poles coming, they are just from the somehow it's the classical transient decay of the velocity,
right,
that is giving this characteristic. 3 arises because that's the exponent of the rate at which the classical velocity decays, a to the minus 3, and I think that's where you get these multiples of 3 in the poles here. So if you had a different kind of ultra slow roll behavior, yes, that might change. Yeah, right. But I haven't really looked beyond the simplest models there.
We're looking into that ourselves. Yeah, thank you very much.
Thank you. There is a question by Nick.
Yes, very nice talk, David. Can I ask how much model dependent are the predictions for the abundance of the primordial black holes in your method?
Yeah, well, they are. I mean, indeed, I've really been calculating the statistics of zeta here, and so actually connecting this to the abundance of primordial black holes is a further step. It's not quite as simple as just the tail of the distribution that I was talking about, but your question is a good question, because indeed, generally these models are very sensitive to the parameters chosen. If you have an ultra slow roll regime, as just discussing with Juan, but typically the simple cases one often sees just this as a transient regime, and you need it to survive for just long enough to give you so these are very sensitive to the parameters often of the model. And the same really I would expect to apply here. I would love to have, one of the things I'd love to do is understand more generic results. The moment we tend to be working with simple linear potentials. So there are the sort of results we find seem to show that you can, for these sorts of models, you can recast fairly general results for the abundance of the tail of the distribution becomes a function, say, of it's basically the width versus the height of the potential. You get a nice sort of dimensionless variable you can characterize the results in terms of. But to be honest, and you would find that the slow roll calculation or the perturbative calculation would also be dependent on that function. But now our abundance would be a different function of that variable. But nonetheless, I think in all these cases, they tend to be they tend to be sitting in the exponent. So the distribution is very sensitive to the precise value of that in in the particular model you're studying. So yeah, so it tends to be very sensitive to the sort of input parameters there. But it would be nice to understand better how generic the results are.
Thank you very much. Very nice talk again. Thank you.
We have a very last question from Rocky Gold.
Hi, Rocky. I can't hear you.
Just like the microphone. Suppose 10 years from now we know the spectrum of primordial black holes. What could you say about the origin, whether it comes from inflation, whether ultra slow roll, chaotic waterfall inflation, or something like that? Do you think you'd be able to work backwards and say anything about the inflation model?
Yeah, really interesting to think about that, isn't it? Yeah. I mean, at the moment, no, honestly. But I think, you know, but you can see that there might be information in, I mean, the obvious thing would be the distribution of masses. I mean, the first thing indeed we'd be interested in is the distribution of masses and, of course, spins characteristic of a primordial population rather than an astrophysical population. But you can well imagine that you would hope to learn about if it is an inflationary process, through the mass spectrum, at least, of the black holes. Of course, it's not as simple as the usual perturbative calculation of the power spectrum, say. But I'd love to be able to write the reconstructing the inflaton dynamics paper from primordial black hole mass spectrum, that the equivalent of the paper you guys wrote in the 1990s, Rocky, on reconstructing from the power spectrum. Yeah, I can see Juan is keen to volunteer.
Hi, Rocky, that was a great question. Actually, let me comment that, of course, you don't only have the distribution of masses of black holes, if you ever measure those, but also you would ask about the special distribution. Now, the non-Gaussian character of quantum diffusion induces a correlation function beyond the usual short noise. So it would say that those black holes are actually clustered to some level induced by this non-Gaussian features. So if you could derive not only the mass spectrum, but also the special distribution and the non-Gaussian properties of the statistical properties of how they're distributed in space, beyond the usual clustering induced by large-scale structure, of course, then you might be able to derive a little bit of these properties of the Gaussian tail, or non-Gaussian tail, sorry, exponential tails that David was describing. So there is a chance that you might have some extra handle due to the special distribution onto what was the actual dynamics during inflation.
Okay, thank you for the discussion. Okay, thanks again. Let's thank again the speaker, and we pass to next talk by Fabio Scardigli. This is Bekenstein bound and uncertainty relations. Are you there, Fabio?
Yes, I'm here. You're
Fabio?
yeah, I'm here. Can you hear me?
Nearer to the microphone, because we hear very, or increase your microphone. I don't know what.
Yeah, it's very, very feeble, the sound, as Massimo says. At least in Zoom, people.
Well,
Yes, now it's better.
now how is it now?
No, now it's low again. There is a problem. Perhaps you have a dynamical regulation of the microphone. This can give some problem. Let's try to mute our. Try to speak. Right?
Yeah. Okay. Okay. I start my talk. Let's see if it works. Okay. First of all, thanks a lot to the organizers for giving me the possibility to have a presentation here at the Corfu Summer Institute. This is a beautiful workshop, and I will tell you something about the Bekenstein bound and the connection with uncertainty relations and the possible generalization of the Bekenstein bound itself using the generalized uncertainty principle. Well, first, well, this is a collaboration with my younger colleagues, Luca Bonifante, Gaetano Luciano, and Luciano Petruzziello. Well, first of all, I want to remind a little bit, say something about the Bekenstein bound itself, proposed by Bekenstein in 1981. Essentially, the idea is that the entropy of a localized quantum system containing a total energy E in a region of size R is bounded from above by an expression like this that you can see on the slide. According to Bekenstein, the universal entropy bound defines how much information can be stored by certain mass energy contained in a region D. The derivation given by Bekenstein is derived by imagining that a capsule of matter is engulfed by a black hole of about the same size, and the increase in the black hole size places a limit on the entropy that this capsule of matter could contain. As you see in the inequality, in the Bekenstein inequality, there is no G Newton, and there is no the gravitational constant, which means essentially that the gravitational self-interaction is neglected, although the Bekenstein bound was derived, as I just told you, via a Duncan experiment involving black holes, so in a strong gravity regime. Another interesting property is the fact that the inequality is saturated by Schwarzschild black hole, by the entropy of the Schwarzschild black hole. It is also important to say that the Bekenstein bound is tighter than the holographic bound, except, of course, when the capsule is almost as dense as the black hole, and then the Bekenstein bound would saturate the holographic bound. Orazio Casini in 2008 proved rigorously the Bekenstein bound using standard quantum field theory in flat space-times. So quantum field theory based, of course, on the standard Heisenberg commutation relations. And what we have done as a first step in this work was to show essentially a direct connection, direct derivation of the Bekenstein bound from the uncertainty relation itself, the standard Heisenberg uncertainty relation itself. And well, we used a very general thermodynamic argument. Given an isolated quantum system localized in a region R and containing, well, the relation between the energy of the system, the entropy, and its volume and the temperature is given by this basic relation of thermodynamic. Now, if we assume the first, the Partition Theorem, so the energy of each constituent of our system is proportional to the absolute temperature of the system, and then for each constituent there is it's valid the de Broglie relation between momentum and wavelength, which we know is essentially equivalent to pose the Heisenberg uncertainty relations. Then, from essentially these two assumptions, well, from the first assumption, you can, in order to be valid the Partition Theorem, you have to suppose that you are close by to a classical or classicality regime in which kT is larger than h bar over lambda. Essentially, the quantum statistics can be well approximated by the Maxwell-Boltzmann statistics. And then our system is localized, so the de Broglie wavelength of the system is smaller than the given size the region R, and taking just these two inequalities, immediately you have this expression here, the derivative using of course the first equation that I presented to you, the derivative of the entropy with respect to energy, which is the inverse of the temperature, is smaller than practically lambda, which again is smaller than R. So supposing that R and E are independent variables, as phase space variables, independent variables, then you can immediately integrate this inequality, and you get practically the expression of the Bekenstein bound. Still, there is of course there is a factor here. There is a multiplicative factor alpha, which cannot be fixed by this very general and very simple thermodynamic argument. Actually, this factor can be fixed and equal to pi with some a posteriori consideration that I will show you in the next slides. The inequality can be still derived also in the hypothesis that there is an equation of state between R and E. So provided this relation is a monotonic increasing function. So the size of the system should be a monotonic increasing function of the energy content of the system itself. Also, in this very general situation, the integration gives essentially the Bekenstein bound, practically derived directly from the hypothesis of the HUP, of the Heisenberg uncertainty relations. It is also possible to do the opposite to some extent, meaning that you can derive the Heisenberg principle from the Bekenstein bound. In particular, you can do this for either massless particles, or considering a particle of rest mass m described by a wave packet of size r, and supposing that this particle is marginally relativistic, which means that the momentum is essentially proportional to the energy of the particle itself. Then the Bekenstein inequality can be immediately recast in this way. As you see, E over C would be just a P and R. So you have this inequality here, Rp greater than H bar half. And here you have the entropy of the system over the pi kb. And therefore, this object will be greater than H bar half whenever the entropy of the system is at least of the order kb. In particular, you can image for an electron with spin up or down as an entropy of kb log 2. So it's order of kb. Well, now, if since the direction of motion of our particle is unknown a priori, the uncertainty in the momentum of our particle is of the order of the momentum itself. The uncertainty in the position of our particle is, as we have said, is described by a wave packet of size r. So the uncertainty in the position is of order r. And immediately you see that this inequality can be rewritten essentially as the Heisenberg uncertainty principle for the particle we are considering. So there is a real very close correspondence between the Bekenstein bound and the Heisenberg uncertainty principle. And perhaps these can explain why the Bekenstein bound has such a general validity. And now, what we have done is, considering the fact that we obtained the Bekenstein bound directly from the HUP. Of course, if you change the uncertainty relations and you go to a generalized uncertainty principle, well, as well, you will have to change also, to generalize, so to say, the Bekenstein bound itself. Before going directly to what we have done in this paper, let me give you one slide of summary about the GUP, the Generalized Uncertainty Principle. This is a research line which has several decades of history. Even started before the war with a paper of Bronstein, and then Young, Snyder, Mead, and Carol Yazzie in the 60s. String theory entered this topic about 35 years ago with Veneziano and Gross, suggested that in a Gedanken experiment on high energy string scatterings involving gravity, the effective uncertainty relation should read in this way. As you see here, you have the standard Heisenberg term, h bar over 2 pi, 2 delta pi, and then there is a deforming term, 2 beta delta pi over h bar, or obviously you can rewrite the formula in this way, in which you see immediately that the standard Heisenberg uncertainty relation is modified by a beta term here. You can arrive to similar conclusion not only via string theory, but for example, considering a Gedanken experiment involving formation of microblack holes in a measurement process, or as Maggiore did in '93, you get a similar relation considering Gedanken experiment involving the Hawking radiation emitted by a large black hole. And these kind of considerations can be summarized by a diagram like this, in which you see essentially the standard Heisenberg hyperbole, which would be there completely untouched if gravity did not exist. But since there is gravity and there is the tendency of gravity to form a clumsy object, to form black holes in particular, then you have also these other, for energies of the order or above the Planckian energies, you have also this other line, which is essentially the Schwarzschild radius of a black hole, linear in the energy considered. And so you have a modification of the standard Heisenberg hyperbole according exactly to the formula that I previously told you. Of course, from a modification of the uncertainty relation, you can write, you can put them in a modification of the fundamental commutators, and then, for example, mechanics, and so on and so forth. As, for example, has been done by Kempf and Mann and Manger. What we have done is starting from these GUP, instead of starting from the usual Heisenberg principle, we have derived a modification of the Bekenstein bound. Obviously, the first thing you need is the fact that since the Heisenberg principle and the de Broglie relation are essentially in one-to-one correspondence, you need to write down a momentum wavelength relation which be consistent with the generalized uncertainty principle. And this has been done about 2 decades ago by Ahluwalia already, 20 years ago. He wrote this generalized wave particle duality, which is nothing else than a deformation beta of the usual de Broglie relation. From here, you can compute the P, the momentum, as a function of lambda. Obviously, if you take the minus sign and if you push beta to 0, you go back to the standard standard de Broglie relation. And at this point, once you have this generalization due to the GUP of the de Broglie relation, you can repeat essentially the steps that we have done on the first slide, again for a system of size R, and immediately you end up with a generalization in beta, deformation in beta of the inequality that I've shown to you on the first slide, on the second slide, which will be this object here. At this point, before going to the integration of the relation, it is useful to distinguish the cases in which beta is positive from the case in which beta is negative. The deforming term of the generalized uncertainty principle is can be in principle can be positive or negative, as it is widely discussed in the literature on this topic. In the case of a positive beta, which means that in that case the GUP predicts a minimum observable length proportional to the square root of beta and proportional, of course, to the Planck length. Then again, assuming R and D as phase space variables, one's independent from the other, and the standard integration initial condition s equals 0 for e equals 0, you can integrate the previous differential inequality and getting this expression, which is our generalized Bekenstein bound. And well, from here you can fix the alpha. You can fix this arbitrary multiplicative constant equal to pi, essentially by demanding that in the limit when beta goes to 0, and of course then the GUP would go to the standard Heisenberg principle, then you want to recover the standard Bekenstein bound expression, and these fix immediately alpha equal to pi. The inequality is still valid also for any monotonic increasing function of the size of the system function of the energy of the system, and perhaps some more physical intuition can be obtained by expanding this expression for a small beta or large r. You see immediately here the correction given to the standard expression of Bekenstein, the correction containing, as I say, the beta, the Planck length, and the size of the system. We can note that this generalized Bekenstein bound lowers the standard Bekenstein bound for beta positive. Here there is a minus. However, the Schwarzschild black hole entropy won't violate these generalized Bekenstein bound, since also the Schwarzschild black hole entropy would be corrected by the use of a generalized uncertainty principle in place of the standard Heisenberg principle. And in particular, we will be lowered too, also this Schwarzschild entropy. So everything is consistent. Well, physically, maybe we can be expected that the existence of minimum length reduces the number of microstates in a given volume, and thus decreasing the total information that you can pack. Then you can it can be contained in a system of a given size. That's the reason essentially of this minus. Again, I say for beta positive.
5 minutes.
Sorry, 5 minutes. Oh yes. There is also the case of beta negative. Well, for beta negative, the things are a little bit weird in the sense that there is no minimum length predicted by the GUP. The calculations are essentially similar, again with the usual assumption of R independent from E. We can get a bound on the entropy of this kind. Again, the alpha can be fixed equal to pi using the limit of using consistency with the standard Bekenstein bound in the limit beta to 0. And again, this inequality holds for any monotonic increasing function of R of the energy E. Expanding for the small beta or large R, the previous inequality, you get a correction, the standard Bekenstein expression of this kind, which is essentially exactly the same expression as before, just that beta is now negative. There are interesting consequences of this, because of course, since beta is now negative, this generalized Bekenstein bound allows the entropy S to exceed, you see here the plus, to exceed the standard Bekenstein bound. And actually, maybe this can be, you can say, wow, so you have violated Bekenstein bound. Well, actually, it's not so crazy in the sense that it's not surprising, since also the standard Heisenberg principle can be violated by the GOP when beta is negative. And actually, this is well, this is a diagram showing the three possibilities. For beta equals 0, you have the standard relation between the entropy and the size of the system, the standard relation of the worked out by Bekenstein. And then here you have the two possible generalizations. For beta positive, you have the orange curve here, which obviously stops to a length, to a finite length, in this case of the diagram to the Planck length, because of the consideration that we have that I told you before. On the contrary, if beta is negative, in principle, you can go even to a zero size of the system. But let me just comment again a little bit on the case of beta negative. We know that the GOP with beta negative can imply the fact that delta x times delta p is just greater than 0. In particular, for uncertainty in the momentum of the order of the Planckian momentum. Obviously, an uncertainty relation of this kind is typical of a classical regime, and this is a possibility. It's maybe can sound a bit strange, but actually, it's the possibility that classical physics, to find classical physics at the Planck scale, has been already explored, for example, by considering H bar as a dynamical field, vanishing for Planckian energy. There are papers on these by Smalling or Maggio and other people. And also very important is the possibility, the even more profound, so to say, possibility that the universe at the Planck scales appears to be deterministic, classical, instead of being dominated by quantum fluctuations. And this is actually the vision at the core of 't Hooft's deterministic formulation of quantum mechanics. So these possibilities are somehow described or encoded or connected at least with a generalized uncertainty principle with a deforming term negative, with a beta negative. Let me go to my conclusions. So we found a consistent correspondence between the Heisenberg uncertainty principle and the standard Bekenstein bound on the entropy of a localized quantum system of a given size and energy. We formulate a generalization of the Bekenstein inequality when both quantum and gravitational effect at the Planck scale are taken into account. As I said, using the generalized uncertainty principle. And of course, at this point, there are many things to be explored, many avenues to be explored still. For sure, would be interesting to study, and actually we are studying possible consequences for the holographic bound for quantum information theory, which is a standard quantum information theory, just based on the standard Heisenberg relation. For black hole remnants, which are a striking prediction of the GUP with beta positive, and also for information paradox. Actually, there are papers on these. I can cite now, for example, the paper of P.Z. Chen some years ago on remnants and information paradox. So I would stop here. I think my time is over, and thank you very much for your attention. Thank you.
Thank you, Fabio. So I don't see in the room any questions online. Yeah, okay, just a very quick question, comment. So you mean for this negative beta case, which at first sight maybe would seem also a bit more unphysical than the other, but actually this would signal this kind of behavior at Planck scale. I mean, a classical behavior. So one should be able to see going up in energy a decrease in the uncertainty in the quantum.
Yeah.
According to, is it correct?
If beta is negative, essentially maybe I can go back to the second slide. Essentially, if B is negative, on this diagram, you would be, instead of being above the standard Heisenberg hyperbole, you would be below. So for a finite momentum transfer, you would get an uncertainty in position equal to 0, so to say, which would be the case in which, of course, if this is true, then when you go to Planckian momentum, or a momentum of order of Planckian momentum, you would get a classical regime, a typical classical regime, where the particle can be localized without any uncertainty and so on. So classical mechanics, so to say, instead of quantum mechanics.
Okay, thank you very much to the speaker. Let's thank the speaker again. We move on.
Thank you. Thank you very much.
Next talk is still online. So we have Anish Ghoshal. Are you? Fabio should disconnect.
I should remove the. Let me see how.
I start to announce the title is Sky meets laboratory via renormalization group equations, Higgs inflation, light dark sector, and gravitational waves from phase transition. I don't see the speaker. I don't know.
Okay. I think it's no more sharing. I'm not more sharing this.
Do you see? Do you see the speaker? So if the speaker is not ready, I think we have ready the other one, the next one, which is just here. But yes. In the meanwhile, we wait for a moment, then we see what. On. Anish Ghoshal, are you connected? We cannot see you. Seems he's not here. We just wait
a few seconds for the next speaker to arrange the equipment here for giving the talk in presence. A bit. No, we don't see the speaker, so I think we are going directly to Gregorio. Okay, so I can announce. Yeah, yes, no, just to entertain the people. Gregorios Patellis, it's quite a long title, is Phenomenology of Supersymmetric Trinification from Dimensional Reduction of n equal 1, 10-dimensional E8 theory, isn't it? So 25 minutes and then 5 minutes questions, you know.
Can you hear me? I guess so. So do it as a slideshow. Present the slideshow. Okay. So thank you for giving me the opportunity to present our work. This is our recent work with George Manolakos and George Panos, and it's the latest edition in a long series of work, but by members of our group that span over 2 decades. But this is the first one that actually has a phenomenological analysis of one of these models. So, indeed, I'm going to talk about the higher dimensional theory, which employs the idea of coset space dimensional reduction, and of course, the motivation is usually the unified description of nature, which could be achieved or tried upon either with extra gauge symmetry, for example, a grand unified theory, or with supersymmetry, or with extra dimensions. These are the most common ones. And the perks of using such or using these methods is that we can, especially with the extra dimensions, we can unify the gauge and Higgs sectors, and in certain configurations, also the Fermi interactions with the above. If we go supersymmetric, as I will talk about in a while, we could unify all the above using one supermultiplet, a vector supermultiplet, and of course, with this theories, you always have less free parameters. So, when you have a high-dimensional theory of capital D dimensions, you have, of course, D-dimensional space that is compactified to Minkowski times the compact space, which is, of course, in D dimensions. If we have 10, we will have 10. This will be 6. Okay, and the naive, the simple idea of the dimensional reduction, in which we want the Lagrangian to be independent of the extra coordinates, would be to discard all field dependence in the extra coordinates. In this way, we simplify our life a lot. But there is a more elegant way in which we don't have to discard this dependence on the extra coordinates, but rather we can compensate this dependence with the symmetry of a Lagrangian. And this turns out to be a gauge symmetry. And this is the main idea of the coset space dimensional reduction, formulated and developed by in many papers several decades ago. So the compact space we choose is a coset space. S is the isometry group, and R is the homotopy group. And we allow a non-trivial dependence of the fields on the extra dimensions and their coordinates. And we impose the condition that the symmetry transformation by an element of the isometry group S of the compact space is compensated by a gauge transformation. So if you can have a gauge invariant Lagrangian, you can also have a Lagrangian that's dependent of the extra coordinates. And this is the general action for the capital D dimensional theory with the gauge part and the fermion part. And the demand that I said before to have this compensation between the transformation by an element of S with the gauge transformation results in some constraints in the fields of our theory. In our theory, it would be the extra degrees of freedom of the high-dimensional gauge fields, which in the four-dimensional theory will be scalars, and our fermions. And the solutions of these constraints give us the remaining gauge group, our four-dimensional fields, and the representations in which they're accommodated regarding to our remaining gauge structure, and of course our potential. So regarding the four-dimensional gauge group, we start by embedding the homotopy group of the coset space into our gauge group, which is called G. Then the four-dimensional gauge group is this one. So it's a centralizer of the embedded homotopy group into the gauge group. Okay. So so this is how we get our gauge structure, our gauge group, our four-dimensional one. And regarding our content, for the scalar fields, we embed the R into S, which is a isometry group. And of course, we want to decompose the adjoint of S, since our scalar fields will be the remnants of our high-dimensional gauge fields, which are of course always in the adjoint representation. So we decompose it like this, and then by embedding R into G and having a similar decomposition, we can match the S's with the R's. And for each one matching, we have a surviving field that is accommodated in an HI representation of our remaining gauge group in 4 dimensions. And it's a similar procedure for the fermions, but not with the S, with the SOD, because that's where they live. So this is the spinorial representation that we decompose. And again, for each matching sigma and Ti, we have a fermion that is accommodated in the HI representation that survives in 4 dimensions. Now, a big discussion, which I cannot fully go into. I cannot go into full extent now, is what happens with our theory that we want to be chiral in 4 dimensions. And it turns out that if we start with capital D dimensions at first of the form 4n plus 2, for example, 10 dimensions, then by imposing the Weil condition, we result in a chiral theory with double spectrum, and then with the Majorana condition as well, we can go to a chiral theory with no doubling of spectrum in 4 dimensions. And all of this happens if we start from a vector-like representation in our higher dimensional theory. We will call this representation F for the rest of the talk. Now, in 4 dimensions, after we integrate out the extra coordinates, and after we take into account the aforementioned constraints that are again imposed by demand of compensation, we get this standard action with our kinetic terms for gauge, scalars, and fermion fields, and with fermion interactions and our potential. And now, the only thing I changed notation-wise is that I renamed these scalars into PA, just to be easier to look upon. And this is the scalar potential of the theory, which is, of course, still in formal form, because we still have to solve one constraint regarding our scalars. Now, this is usually a tedious procedure, but if the isometer group can be embedded into the gauge group, then we have a shortcut there, because when we reach our four-dimensional gauge group H, we have spontaneous symmetry breaking, and the H, which was the centralizer of R into G, further breaks into a smaller gauge group K, which is the centralizer of S into G. So this is why it only happens when S is embeddable into G. So we have a spontaneous symmetry breaking just after the dimensional reduction. Now, in our, this was the general framework. Now, in the model that we will analyze, we have a 10-dimensional model with n=1 supersymmetry and the E8 gauge group. And our selected coset space is a nearly Kähler manifold SU3 over 2 U1s. Okay, this is a non-symmetric space that admits torsion, which is important. I will talk about this in a while, and can admit different radii. This is very important for our phenomenology, and it has the perk of preserving the structure of our supersymmetry multiplets. You cannot state that it preserves exact supersymmetry, but it also naturally produces, with the dimensional reduction, soft supersymmetry breaking terms. So when you go to your 4D theory and eventually you have to break SUSY, you don't have to have an ad hoc sector, soft sector, in order to do that. Now, this is the application of this here. So from E8, we try to find an embedding of the R, which is U1 times U1. So E8 can be decomposed as E6 times SU3, and once again as E6 times U1A times U1B. So this is our R, and since it's abelian, the four-dimensional gauge group will be its centralizer into E8, which is the same. It's E6 times U1A times U1B. But since S is embeddable into E8, we have a spontaneous breaking after the dimensional reduction down to E6, okay? And the U1s remain as global symmetries. Now, before we go to K, when we have our H group before the spontaneous breaking, we have this E6 times U1A times U1B, which is an n=1 theory. And we have, of course, our vector supermultiplets for our gauge bosons. And we have three chiral supermultiplets, the indexed ones, AI, BI, CI, which are accommodated in the fundamental of E6, which is 27. And they have their respective U1 charges. And another three chiral supermultiplets non-indexed, which are singlets under the E6 group and only have charges under the abelian ones. Okay. Now the comment about the torsion is here, that our unified gauge unit mass has a purely geometric origin. Here are the three radii that we have, and this is the contortion. So by an appropriate choice of torsion, we could have TeV level, TeV scale gauge unit mass, which is very important again for phenomenology. Now, this is the potential of four-dimensional theory. There is a geometric term at first, and then we have F terms, D terms, and soft terms. Now, the D terms have contribution from the E6, from the U1A and the U1B, and they're of this form. Of course, this is scalar potential, and these alpha, beta, and gammas are the scalar components of the indexed A, B, and C's, and the unindexed ones that you see here of the singlet representations. So this is the form of the D terms, and I won't go into much detail here due to the time restriction. We have our F terms that match the concept that they result from an assumed superpotential of this form. And of course, we have our soft terms. We see here, here, and here. These are the squared soft scalar masses. And the fact that we have a minus here is very important. I'll talk about it in a while. And we have our soft trilinear terms, which again have geometric origin. Now, when we break the H to K, due to this fact here, is this perk. We have to give webs to some of the singlets in order to break the 2U1s. And you have to give webs to at least 2. We choose the alpha and beta scalars of the 2 singlet representations to acquire webs and result into any 6. And the fact that these remain as global symmetries has serious implications good and bad to our phenomenology. Now, we are left with any 6 though, and we want to break it further in order to result into the standard, what time is it? Into the standard model. So we will break further with Wilson lines. So instead of having the SU3 over 2U1s, we will name it B0, and we will replace it with B, where B is the B0, the Coset space we had, over a freely acting discrete symmetry of B0. It will be Z3 here, and this will break H not to K, but to K prime, which in our case will be the tonification group times the 2U1s, still n equal 1. And when we want to see what survives from our matter content, we go into some detail here, but let's just sum it up quickly. From each of the 27s, so the chiral supermultiplets that are not singlets under the E6, they are decomposed from E6 to SU3 cube as this here. And the Wilson lines leave 1 for each of them. For the A chiral supermultiplet, it leaves this one. For B, it leaves this one, and for C, it leaves this one. So we had 3 chiral supermultiplets, and now 1/3 of each survives, and altogether they make 1 27 supermultiplet. Okay, and regarding the singlets, only the C survives. Okay, which is singlet under all SU3 groups, and only has a U1B charge. So now we have 1 27 chiral supermultiplet and 1 singlet. But we want to have 3 fermionic generations. So instead, we will use some non-trivial monopole charges in R. These are very nicely related and outlined in Dolan's paper in 2003. And we can indeed result in 3 copies of each. So we have 3 psi1, 3 psi2, 3 psi3, and 3 Cs. I renamed them because it follows all references follow this or this terminology. So the first one and the second one have our 2 quarks for each generation and 1 new exotic quark, which will get super heavy when we break this gut. And the third one is a lepto-Higgs multiplet. These are the lepton content plus its right-handed neutrino, a sterile neutrino-like particle here, which will get super heavy, and 2 Higgs doublets. And for 1 generation, this is the form that our potential makes. So we see here that M3 squared are soft masses that concern our leptons and our Higgses have this minus here. Okay, this is it, and this will be important. Now we can further break our SU3 down to our supersymmetric standard model gauge structure, and again we can further use 2 Higgs doublets to break it into the standard model. Now, what's our choice? What choice did we make last year in order to give phenomenology to this model? You see that the trilinear terms are of order 1 over r, and the scalar masses over the order 1 over r squared. Now, we can either choose large radii, and if we do that, we have to include Kaluza-Klein contributions. Okay, so we have to know the eigenvalues of the Dirac and Laplace operators, which we don't. So this is a problem for further study, for future study. Or we can choose small radii. Then we will have a high scale breaking. Or since this space can admit different radii, we can make a very specific configuration for the radii. So one of these three scalar masses become of TeV level, while the others stay at gut level. Okay, so we have the soft mass that concerns leptons and the Higgsino mass parameters to TeV level, and we have our squarks and soft trilinears at gut level. Okay, and in this scenario, we have selected R to be around 1 over mgat, so the compactification scale matches the mgat, so there's no running in the SU3 cube model. And after the gut breaking, the potential is of this form. So we have the VEV of the scalar of the third generation of theta, which is the C that are named theta. So these are the singlets. This will take a VEV at the order of the TVs, while the other two will take VEVs at the gut scale. Now, we need this because the U1s forbid the lepton Yukawa terms, and we also don't have new terms, okay, in our superpotential. So these are solved with the introduction of higher dimensional operators. Here, the K bar is the VEV of the conjugate scalar component of either SI, neutrino right I, or theta I, or any combination. So this can reproduce lepton mass hierarchy. And the mu terms, now, for the third generation, so for 3 and 3, we'll choose here theta bar 3, which has a VEV of the order of TVs, while for H1 and H2, we will use theta 1 and theta 2 respectively. So the mu term of the third generation of Higginos, because we have 6 doublets, 2 for each generation, will be at the TeV level, while the others will go supermassive. So we have here our soft trilinears gut level, squarks gut level, leptons TeV level, soft Higgs masses TeV level, third generation of the mu term TeV level, the other two are gut level, and the unified Higgsino mass with the correct selection of torsion will go again at TeV level. So this is a split-like scenario. It's not the standard split SUSY scenario, but it's a split-like scenario. And we have to see what happens with unification of the 3 gauge couplings when we break the gut into our split supersymmetric standard model scenario. Now, we use an intermediate scale at around 1 or 2 orders below gut in order to allow them to allow all these gut scale fields to decouple more naturally. And it turns out that, and again, we run down to TeV. After the TeV scale, all the low SUSY parameters decouple, and we go down to the electric scale. Okay, so using A1, alpha 1, and alpha 2 as an input, we predict the strong coupling within the sigma of the experimental value for this selection of scales. So the gut is at around 10 to 15. The intermediate scale is 1 to 2 orders of magnitude below, and the TeV scale is around 1.5 TeVs. Now we can do this selection because the U1A charge is a parameter times a factor times the baryon number. So we don't have any process that induces proton decay. So we can indeed keep this value. Now, when after the gut breaking, when you examine the Higgs potential, the 2 Higgs doublet Higgs potential, and you compare it with the standard 2 Higgs doublet potential, you get that the lambda 1, 2, and 3 are 20 times G T square, which this is the unified gauge coupling. The L4 is something similar, and the other 3, as expected in a supersymmetric Iverbergian theory, vanish. Now these relations are gonna be boundary conditions at the GAT scale. So these are the three. The G3, of course, will be we have the boundary condition of the gauge coupling, and the two Yukawas, since we had one vector like supermultiplet at the start with only one free parameter, the gauge coupling, these Yukawa couplings have the same strength. Okay, so the Yukawa couplings of the top and bottom at the boundary, the GAT, are G. Okay, and I should mention that this analysis is done only for the third generation at the moment. Okay, so we only take into account top and bottom Yukawas, and these are some threshold corrections that we use since we have a flat way of decoupling particles, and we did a one loop analysis as a preliminary one, and we have the bottom mass at the Z scale within 2 sigmas of experimental value, and the top pole, the pole top mass again within 2 sigmas, and the light Higgs boson mass is predicted within 1 sigma of the experimental value. Now, since the Yukawas are the same in the GAT scale, it was expected that we will have a large tan beta. The CP-odd heavy Higgs is between 2 and 3 TeV, so this is okay for a large tan beta, and we expect the LSP to be around 1.5 TeVs. So to conclude, we had a special choice of the coset radii in order to have a split-like supersymmetric 2 Higgs doublet model below the GAT breaking of the trinification group that resulted from the dimensional reduction of the n=1 E8 over the compact space SU3 over 2 U1s and the Z3. We had one loop predictions in agreement with experimental observables. We expect an LSP around 1.5 TeV, and we are already planning our two loop analysis, and we want to reduce the full Sosi spectrum and apply many constraints like the bit physics constraints. And we have also planned to go further and investigate whether we can accommodate the dark matter into our model, especially when if we have the lightest neutralino as the LSP. And we could, of course, probe its discovery potential in future colliders. And one more thing is that we also examine its high energy potential to see if it's in agreement with the observed value of the cosmological constant. So thank you very much.
Thank you. There is a question by Professor Buccella and another one by other two. Okay. 3.
I would like to know which is the mechanism for reducing the symmetry from E6 to the standard group. Is it traditional with Higgs or is it
No. No.
And the second, if your approach, baryogenesis is predicted.
So I didn't get the second one.
The second one, if your approach, there is the possibility to have baryogenesis to leptogenesis.
Well, this I cannot answer. But the first one, no, we break the 6 with the use of Wilson lines. So instead of taking our original coset space as a compact space, we have this Wilson flux breaking mechanism that reduces E6 to the trinification model. And since when we have our trinification model, then we follow by a standard gap breaking, a spontaneous breaking.
Next question, yeah.
You had this extra Higgs-Zenos, and you said the corresponding new prime parameters order GAT scale. But if understood correctly, in these representations, there are also the fermions of the standard model, the first 2 generations. So how do you get those light?
Okay. Yeah, sorry. δεν έχω control όμως. Okay, so this is the multiplet we're talking about.
Exactly.
And let's say this, we take the fermionic counterpart, okay? So these are the Higgs-Zenos, let's say, of the first generation, okay? So these are the ones that get super heavy are the mu terms, not the soft masses.
No, this I understand, but the same multiplet, you only have the Higgs-Zenos together with the standard model, let's say electron or muon. And why is the mu parameter only for the Higgs-Zenos but not for the complete multiplet L?
Well, you can take if I understand the question, you can admit the higher dimensional terms after the breaking. So they're not together anymore.
But this is but you have SU3 cube at this scale, at the gut scale. And you apply, you have this mu prime, so this mu parameter, is this induced by the breaking or is it before you break SU3 further?
After.
Okay.
Well, if you apply it before, first it will be how you say, and the Slepton mass parameters of the first and second generation will go super heavy as well. Okay, so this is just regarding this is a qualitative approach. Okay, so I can
sorry. I think one last question, because then we have the other talk.
Yes.
Now the speaker is there. Oh, was Frampton?
Yes, hi. So, sorry because I missed due to I confused the time zone. Actually, I'm in a different time zone, which is one hour behind. So I thought it was the same time zone.
Because
sorry.
we have a question here from in the hall. Just the last question from Professor.
Yes. Can you show the quark spectrum? I think it's maybe on that slide. But did I understand in each?
You mean here?
In each family, you not only do you have an exotic quark?
Yes.
And what are the charges of them?
So you mean this one?
This one, yeah.
This is a down-like. It's regarding its charges, it's like the down type quark.
Minus a third. And it's
Yes.
a color triplet and spin half.
And it's what?
It is also a color triplet on the spin half like a normal quark, but its mass is TeV?
No, its mass, it's gas scale, because when you break the SU3 cube like this, these allow it to get supermassive, because these waves are the gut breaking waves at the gut level.
You have some extra quarks at the gut scale.
Yes, and these are what are more. These are the more important here. The reason when you take the intermediate scale, these are very important in the running of beta functions between the gut scale and this intermediate scale that you consider them to decouple below of.
Nevertheless, you would have some baryons and mesons at the gut scale from QCD binding. Excuse me? Yeah, well, can you let the speaker answer, please? Go ahead, answer.
Sorry. Yeah, you could have.
I'm sorry to interrupt this interesting discussion, but we really have to move on for the next. Let's thank again our speaker. So Ghoshal, Anish Ghoshal, are you?
Yes. Hi.
You should screen.
I think it says I cannot share while the other participant is sharing the screen. So maybe okay.
Yes. So
I tried. Can you see my screen?
Okay, so we have your title over there, I think. Okay, Skynet's laboratory. We have read already before. We are normalization group equations, Higgs inflation, and the light dark sectors. Please stay in time at 25 minutes from now. Yeah. because we are very late. Yeah.
Okay. So sorry. Thank you. So first of all, I apologize for the delay in my talk because I actually got confused with the time zone. I'm actually 1 hour behind the Greece time zone. So I apologize for that. So I'm going to speak about Sky Meets laboratory via RGE running. And I'm going to focus on 2 different aspects. One is inflation and another is gravitational wave from phase transition. But both of them are linked by the same fundamental idea that you can relate observables from the sky, which is basically the CMB or the gravitational wave, with the observables that you measure in your laboratory physics, like lifetime of a particle and stuff like that. If you use the real motion group running, and of course you have to do it in a proper BSM or a standard model kind of thing. Okay, so can you see my scrolled slide, the next slide as well? Is it working?
Hello? Yes, we can see you very well.
Okay, thank you. Yeah. So my outline of hello.
Oh, it's okay. It's okay. We mute when we just do not create extra noise. Please go on.
Okay. Thank you. So yeah. So this is the outline of my talk. I'm going to say about how the UV and the IR physics is connected via the RGE flow, and this provides us with the complementarity probe that I talked about. First of all, the first part of talk is based on a simple model of inflation that can have this property, and the model of inflation is basically an inflection kind of model of inflation. Then I'm going to talk about it can possible to do various other kind of model building, like dark matter neutrino or flavor or even flavor fields kind of model. So this is the story of the standard story of the universe. We believe there was a big bang, then the universe expanded exponentially, then at some point of time the radiation domination happened, matter radiation ecology, then the photons decoupled at some point of time, which we observed as CMB, then the stars and galaxies formed, and we see the non-linear structure that we have today. And if there was some early universe before big bang nucleosynthesis, gravitation wave and inflation are the ways to probe the universe. So cosmic inflation, as we know, it is characterized by a quasi-de Sitter expansion of the universe, and it solves the horizon problem, flatness problem. In the usual slow roll approximation of inflation, we know that one of the typical ideas is that you introduce a scalar field in early universe, then it has a potential where it slowly rolls down and basically gives rise to a vacuum energy kind of state, which gives you this exponential increase of universe, and then you have to match with the CMB observables. So the recently measured CMB observables from the Planck satellite, which is known as the observers that you want to match are known as the curvature perturbation amplitude, the slow roll parameter, which are the spectral indices for the scalar and the tensor modes, perturbation modes, and these constraints to be valued to be very small. As you can see, the ns to be 0.96, which means that you have a scale invariant spectra, and there is only an upper bound. You can do it in a plot like this. This is a plot of ns and r, is standard, and then you can take various potential for this scalar field and try to see which you have some predictions, and Starowinsky model and the Higgs inflation model rise very nicely with this kind of prediction. This is the standard story, and these are exactly how you relate with given a potential. You relate the first derivative, the second derivative, third derivative to this kind of various observables, which in turn goes to this r and ns and also the running of the spectral indices that I talked about in the previous slide. So this is how it happens. You have a scalar field, it rolls down, and then at some point of time it decays, gives rise to the universe and radiation. Okay, so now coming to the model of inflation, we all know that one of the very well motivated ideas is that you take a potential of a scalar field, and then you introduce a non-minimal coupling, typically of the form of xi phi square, or you can have other kind of potential, and one very nice example is of this potential is a quartic potential lambda phi 4. It can also be the standard model Higgs or any other fields beyond the standard model which has this quartic kind of potential. Quartic potential is also motivated from quantum field theory sense, because you do not have quadratic. You do not have m squared phi squared terms or quadratic divergent terms. It is the only renormalizable conformally invariant operator you can write for a scalar field. Okay, so now if you do this and then you go through the entire process of calculating the NSRR, as you can see, these are the predictions for what values of non-minimal coupling and the quartic you will be able to satisfy NSNR. What we observe is that the non-minimal coupling will decide this scenario, and there is no direct sensitivity to particle physics model building of the web, because this no matter what lambda you take, you can tune the non-minimal coupling and you can match with the CMB values. So the question that we wanted to ask at this point of time is that, can we have a scenario where there is one-to-one correspondence between particle physics properties like coupling or a mass of a particle and the CMB NSNR values or we observe, so that we can break this kind of degeneracies that we often see in cosmology. And this will be in the similar spirit as you do, for example, a typical relic density calculation or a baryon asymmetry calculation, where you have the coupling or a mass with some properties, because you have a cross section there. So you can usually relate your couplings for particle physics to an observable in cosmology, like relic density of dark matter or baryon asymmetry. But here we do not have the advantage of having a cross section. So how to do this? So one of the ways we found out that can be done is to have and for example, to show in a very simply in an inflection kind of model, and the model of inflection point inflation is very simple. So you make the first derivative and the second derivative to very small, and you know this is the reason why your slow roll parameters will also be satisfied, which are very small, observed by the CMB. And then you expand the potential around a particular field value, which here we call M, capital M, which is, we call this the inflection point. And then you can, depending upon your coefficients, the coefficients of your expansion, V1, V2, V3, you can get this flat region, and especially it will be dominated by this cubic term, because cubic term will give rise to the sharp, flat, and then the sharp increase, which will by which you can make the inflation happen. And then going through the process, you can relate these coefficients to the inflection point, and of course these these are V1, V2 are the coefficients of the cubic, the expansion around the in inflection point. And then you of course you will have a constraint on this V1, V2 from your slow roll parameter models. Okay, so far so good. We have an inflection point of model. We can relate all the coefficients. Now the question comes how to relate it to a particle physics potential. So for one of the question is, can such a model play such a role? The answer is no. I will come to that later. But any BSM Higgs which you can motivate from giving the neutrino mass, or from flavor physics, or from having strong CP problem actions, or even from dark matter physics, you can have any BSM physics. So which can play this role of inflection point inflation match with what is I'm going to say about. Now for this, I want to show it in a very generic U1 extension model, where we only extend the standard model with one gauge particle, one scalar particle, and one Yukawa particle, just for model purpose sake, that how the dynamics works out in the dark sector. But it need not be this U1 extension. It can be done in any kind of extension possible. And one of the best example is of course the U1 B minus L model, which is motivated from gauging the approximate global symmetry we have in the standard model. And these are the particle constant. You introduce 3 right-handed neutrino to give the right neutrino mass. You introduce 1 phi extra BSM Higgs, which will play the role of our inflecton to break the U1 B minus L. It gets the mass, and then you also have a gauge boson corresponding to this gauge U1 B minus L, and then everything is nicely linked up, the masses of the neutrinos, gauge bosons, and the inflecton related to the web, and the coupling, the gauge coupling, quartic coupling, and the Yukawa coupling that you have in your theory. And similarly, you can make it more general for U1x. Then you basically have an arbitrary way of, because in the B minus L case, you can see all the particles in the sun model and the BSM sector are having the same kind of charge, universal charge. Here you have a more freedom to play with the charge, because those have become free parameter. Okay, so we take again the quartic potential, but now we observe the fact this lambda is not a constant, but is a running due to the quantum corrections present in your theory, namely quantum corrections from the extra gauge boson, and the quantum correction from the extra Yukawa sector, and of course from the standard model sector. Now if you do that, then and if you look at how so what happens is that you can replace this lambda by the RGE, which in turns goes in your expansion of the inflection point v1 v2, and you will have the relation between the v1 v2 with the beta functions of your theory. In the beta function of your lambda, you can see the extra gauge coupling contributes and the extra Yukawa coupling contributes. And at some point of time, what you want to do for the for getting a very for matching the CMB, you want to make the lambda very, very small. You want to reach a point where, due to the running effect, that even if lambda is not so big at the tree level, but due to the running, the lambda can be reached at some point of time, this inflection point kind of scenario where lambda becomes very, very small, and you can match with the CMB. And if you do that, then so how does this happen? So as you can see, in this scenario, the beta function is basically governed by the fine balance between the gauge coupling and the Yukawa coupling. Yukawa coupling contributes negatively, and gauge coupling contributes positively. And they themselves, if you look at the beta function of the gauge and the Yukawa, they themselves do not run so much. So we want to go to a scenario where the gauge coupling, Yukawa coupling are cancelling between each other, and this inflection point is created where you match with the CMB. And so basically the exact potential is a logarithmic improved lambda 5 for each potential that you can see. So as you can see on the left of the plot, this is a plot of lambda versus the RG scale, which is the phi scale. And you can see as it goes in the high, it's scaled with respect to the inflection point, of course. As you go in the high energy region, at some point this become very, very small because of the running of the Yukawa coupling. And then here the balance happens between the gauge and the Yukawa coupling, and then you increase due to the increase of the gauge coupling in the UV as well. And this results in the lambda 5/4 logarithmic potential to this flat region. Where this happens, you get the flat region, and you can of course match with the CMB and etc., which I do not want to go into details because I've already said how these flat regions of inflection point can be matched. Now what happens is that now there is a precise prediction in your coupling, in your particle physics BN model, that what values of gauge and Yukawa in this model, but it need not be gauge and Yukawa, we can do it for any model, that this inflection point condition will happen. And not only inflection point needed to match with the CMB can happen. And the relation that you obtain is basically this, which is a relation between a gauge and the Yukawa couplings. Now, so far so good. We know how to test this kind of models in our laboratory observables. You basically go on to calculate the right-hand neutron, the heavy neutral lepton mass, the inflecton mass, the gauge, the Z boson mass, as you can see here, which becomes, of course, determined by the Yukawa coupling and the gauge coupling times the web of the BB minus L theory. And if you do this, then the standard way of searching for Z prime in this model can be utilized, the Drellian process, and basically you will have this prediction of so you can basically plot in which regions of your searches from Atlas and CMS or other Z prime searches can be mapped with your inflection point condition in your CMB, because every point will correspond to this gauge and Yukawa coupling value. But before showing you the final result of the plot, I just want to make how the reheating happens in a very standard procedure. The phi decays to standard model procedures, and we can estimate the reheating temperature. We want to be below the BB, above the BBN temperature 1 MeV, and we will have an extra constraint or whether that gauge coupling or Yukawa coupling will correspond to that or not. Okay, so this is one of the results which I'm showing. This is a plot of the search of MZ in your various collider experiments of high luminosity LHC, which will happen late in the upcoming years, and the bounds which is already ruled out by LHC, as you can see here. And then in this plot, you can see so what values of this in inflection. Hello? Yeah, can you hear me?
Yes, we can.
Oh, sorry, I just got a notification saying the recording has stopped, so I just got confused with it.
Yes, okay. Yes, indeed. Recording has stopped, Massimo.
Okay. So should I wait or should I go
I think so, because it might be a network problem of the local host. I'm remote myself. So if you could just wait, because I lost connection with the... Please, can you just wait? It's not your problem. It's a network problem. Sorry.
Okay.
While we're waiting, Anish, could I please ask you to put your slides on the
sure.
website? Yeah, it'd be
Okay,
really
sure,
good. Yeah, because you're going through them quite quickly, and it's very interesting. Thank you.
Sure. Okay. Sure.
Yeah, yes, indeed. That's a very good suggestion. Thanks.
Sure. I'll put them after my talk. Sure.
I will send an email to the local organizers to see what's happening. It's probably a network problem.
Okay.
Apologies.
I think it started, right?
Yeah, now it's you can resume, please.
Okay.
Yes.
And everybody hopefully.
Now we see you. Sorry, there was an interruption here. So if you can rapidly come, you were a bit before with the.
Right. Okay. So maybe I start from here again. So I just summarized that we obtained the condition in your BSM model building. What condition gives you the CMB? And that basically translate into your laboratory Femology, which is in this case is a Z prime search. And Z prime search will give you constraint on your parameters page, which is already ruled out by, for example, LHC, and in which you can search in your future high luminosity collider or other kind of physics. And this diagonal lines represents the reheating temperature, as I told you. This diagonal line, for example, represents reheating temperature of 4 MeV probably. And as long as you are below this diagonal line, you are okay to satisfy the reheating temperature. So so far so good. I don't want to go into details, but as I try to convince you, for any kind of dark sector physics where you have this kind of nice cancellation of a beta function, this can be done. You can also incorporate dark matter candidates. You can incorporate right-handed neutrino masses, which are needed for your smallness of your neutrino mass. You can do flavor physics and this kind of stuff. And I've been exploring some of this. So I don't want to go into details here. And of course, all this will also translate in your various kind of laboratory probes that you have. Here, I only showed you collider Z prime searches, but depending upon your model building, you can do lifetime frontier searches, intensity frontier searches, even neutrino searches as well. Okay, now let's, I just want to say a few words of this part of my talk before I go into the gravitational wave sector. So I tried to convince you that the ultraviolet is connected to the infrared via the renormation group equation we're running. We can do complementary probes of BSM model via light dark sector experimental searches and the CMB, and also not only light dark sector, other kind of experiment as well. I put light dark sector because these are very light particles, which we were saying the fields were very pretty light compared to the very high, I mean, the early universe scalar field that usually people talk about in cosmology. Now, standard model cannot play this role, I told you, and the reason is because standard model gauge coupling is already determined to be very, very high. So as you typically noted here, this gauge coupling needed to be very, very small because of this cancellation to happen, so that the potential becomes flat, or else you end up having lots of corrections. The potential does not become flat, you cannot do. So standard model hits cannot play this role, but any other dark sector introduction with such and such properties which I showed you can do it. And and as I showed you, this can also lead to various other kind of laboratory field. You can imagine to hunt. So here I showed you to hunting for the Z prime, but you can imagine to hunt for the inflecton itself. If you do not have, I mean, you can search for the scalar particle itself, right? And just it can be shown as an inflecton as long as you satisfy those properties and CMB happens. So plethora of particle physics model building directions are possible now involving dark sector and the CMB. And now we have a one-to-one correspondence that I was alluding to. With the particle physics couplings and the CMB. Okay. Now I just move on to the next part of my talk, which is in the similar spirit that yeah.
Because we are very much just 5 minutes, if you can make it.
Okay. I thought I had 25 minutes, so and I got some break in between. So
all sorts of okay. Try to stay in.
So maybe 10 minutes, because I stopped for 5 minutes actually due to the problem in the connection and the recording. So if 10 minutes is okay for you.
Yes, 10 minus 7 perhaps.
Okay. Okay, so here the idea is going to be the same. The UV and the IR is connected by the RG, but the cosmic observable is going to be the gravitational wave, amplitude. I don't want to go into the details of various other gravitational waves, but for here we focus on gravitational wave from phase transitions, which is again very much related to how strong this phase transition can happen. Depends upon the particle physics coupling, and I'm going to show you how that can lead to these complementary signatures as I showed you. Okay, so in order to understand phase transition, we need to understand the quantum field theory at finite temperature, and typically what happens if you take a tree-level scalar potential, you introduce finite temperature corrections coming from your bath that you have in a plasma if you have the sun model, or in a BSM theory, and then at some point of time this potential may develop a thermal barrier, and the field can tunnel from one minima to another minima, from false vacuum to a true vacuum, and due to this you can get your from your plasma you can get rid of this delta V, the energy density, into your background. And this background energy density can be seen as the stochastic background of gravitational wave. You have converted the thermal energy to your gravitational radiation, basically. Now, this has to be very strong enough. Delta V has to be very, very high in order to be observable, detectable. This is not possible in standard model because of the couplings and the gauge couplings we have. But in BSM scenarios, it is possible to make this strong enough to be detectable. Now, involved studies are needed to how this kind of scenario happens. Bubbles, walls, nucleate. There is an expansion on the plasma. There is also magnetohydrodynamics effect. We cannot go into details of that, but usually if you do it in a very naive and approximate way, there are standard ways of understanding how the spectrum of the gravitational wave looks like from the simulations that people have done. And usually there are three contributions from the bubble wall, sound wave, and the magnetohydrodynamics of it. And there are three quantities here which one wants to have to keep in mind. One is alpha, which basically gives you the amount of radiation that the thermal energy got translated into gravitational wave energy. The beta is the time during which the phase transition happened. It's a very long time or a small period of time. It is related to the theory, the potential and the action of your theory. And thirdly, you at the temperature at which this bubble nucleation and the phase transition started to happen. So given these three quantities, alpha, beta, and T star, you can go on to calculate the gravitational wave amplitude, and it basically scales like this, which I am showing you here. The H star being the Hubble at which this phase transition started to happen, the size of the universe at which this phase transition starts to Hubble. And given any theory, given your particle physics theory, BSM theory, you can go on to calculate the alpha, beta, and T star because it follows very simple relations as you can see here. You have to actually do the bounce calculation, which you usually do it in numerically, but you will have the predictions of alpha, beta, and T star here. Okay, so and how this translates into gravitational wave amplitude is the following. This is a plot of, on the y-axis is the amplitude of your gravitational wave, and the x-axis is the frequency, and you will have various detectors there, LISA, LIGO, and the other detectors here. So the alpha parameter I talked about controls the height of your spectrum. This is the prediction of a spectrum, any typical spectra. Black line actually denotes the spectra coming from the bubble collision. So alpha controls the height. The T star at the temperature at which the phase transition happens, that the peak controls so the particle value corresponds to a particular peak, and the beta basically acts as some diagonal translations here, because it maps how much the duration will happen. So you can go in both the directions here. So the model I just wanted to show here is an axion model where you have a very high scale scalar particle sitting, and you have a phase transition in the UV. And we all are familiar with how the axion solves the strong CP problem. The radial, so you must remember the radial part of the axion is the phase transition is in the UV, and that's what I'm looking at here. And the phase part, so we have a complex scalar which solves the phase part, solves the strong CP problem and the axion. And the radial part is responsible for the phase transition that I'm trying to show you here. So now. And the usual process is like you write the tree-level potential, you write the one-loop potential, you do the finite temperature corrections which involve processes, and then you can go on to calculate the alpha, beta, T star, which I showed you here. If you go through the entire process, you can have predictions of your alpha, beta, and T star, and from your particle physics couplings that I showed you in the in the potential here, the couplings of K, kappa, and the quartic couplings, you can get it on the plane of the on the plane of the gravitational wave plane. These are various detectors, and these are predictions of various couplings that you have in your theory. Now, the scale at the peak frequency determines the Petrie-Quinn scale. And this is, as I showed you, these involve the one loop running. And this is the point I want to bring back again here. The RGE connects again the UV physics with the IR physics, the cosmology of gravitational waves with the particle physics property. And you can basically you can translate this into your laboratory and astrophysical action searches, which is a plot in your action mass plane and your action coupling planes to your photon in this case. And here you can see these are various action searches, the green and the yellow and the blue. And the pink region here, the magenta region here, is what the Big Bang observer LISA and the LIGO can be probed. I mean, we'll be able to probe this region of the parameter space, again related, as I told you, related to the one loop running and the particle physics couplings you write here. So this translates to a probe of your Petrie-Quinn breaking scale, or the action, in this case, the action like particle decay constant. And these are various detectors, if you can see on my screen, LISA, BBO, DESIGO, MAGIS, which scales it can probe. As you can see, these are very small scales, 10 cube GeV and 10 to the power. This is a range which LISA can probe, for example, go up to 10 to the power 8 GeV, and as low as 10 to the power 3 GeV. And this complements the RG thing that I was trying to say to you, that we have observers from the sky and we have observers from the laboratory, which go in hand. So I don't want to go into details of the models anymore. I just want to conclude. Before that, I just want to show you a typical plot. So in one of the models I studied, which is again related to the RG and a very particular way of understanding the action model for a typical action decay scale. So this is the Petrie-Quinn, classical Petrie-Quinn decay scale, 10 to the power 9 GeV. We'll have predictions in the gravitational wave of the order of 10 and 100 hertz, which is here. And these are very high amplitude gravitational waves because of the model that we take is a conformal model. And if you do the calculations, you will find the amplitudes are very, very high. And this is controlled by alpha, as I showed you. And these are various detectors that controls your sensitivity. GS is basically, again, one of the couplings that you had and modified due to running. Okay, so I tried to convince you there is a complementarity probe between the sky observables and the laboratory observables. Gravitational wave detectors will be probing the pre-Big Bang nucleosynthesis era, and any UV completion action or dark matter, it will be sensitive to your laboratory and astrophysics searches, but also makes predictable predictions in your early universe dynamics. Gravitational wave from strong first order phase transition from in this case Petrie-Quinn symmetry breaking, which is very high, 10 to the power 9, 10 GeV for typical classical action, will be testable. I didn't have time to go into details of how conformal symmetry breaking makes gravitational wave high, but just to end, gravitational wave era invites us to dare and imagine proposed test of UV completions in the BSM sector involving quantum field theory and gravity. Thank you.
Thank you very much. Yeah, we have a question from Northampton. Just a moment. Okay.
For the primordial gravity waves coming from inflation, what would you predict are the wavelengths typically?
So for this, I mean, for the Petrie-Quinn phase transition scenario or the Higgs in inflation scenario?
Find evidence for inflation itself.
Yeah, okay. For the inflation itself, the number is very, very small. As I showed you, the R, the tensor to scalar ratio R in the model, it's very suppressed and it's very, very small. It's 10 to the power minus 6 actually, the value of R at the CMB scale, because R is let's see if I have the relation of R here. So basically epsilon will control my R, right? So my epsilon is given by my first derivative. So here the V1, as you can see, is pretty small. So it typically corresponds to R of the order of 10 to the power minus 6 in the inflation thing. So if you measure it at the CMB pivot scale, which is 0.05, okay, then it's very, very small. But again, you have the freedom of using the RGB. So in the UV, which means at very smaller length scales or very high K values, where you do not have the CMB but other gravitational detectors, you can probably boost the gravitational waves as well. It's depending upon your first order scalar perturbations, how you're boosting.
CMB, but about detecting the gravity waves in a gravity wave detector like LISA or something like that. What would be the wavelength for these primordial gravity waves coming from?
So that we have not calculated, because you need to solve the full Mukhanov-Sasaki equation for that in order to obtain the full power spectrum. Here we just only focused on NS and R, which the CMB measures. But if you solve the full power spectrum for this kind of inflection point potential, it is usually you can tune this because there is an inflection point here. So as you can see in the UV, the potential gets a huge boost. So depending upon how your inflection point behaves, probably you can boost this primordial gravitational wave and make it detectable in LISA. So we didn't do the full Mukhanov-Sasaki for getting the power spectrum. We just simply concentrated on NS and R for the time.
Okay, thank you.
Okay, so let's check if there is any question online. Doesn't look like. In this case, just to be sure. Okay, so I think we can close the session. Thank the speaker again. Thank all the speakers of this session, and we see you again at 4.
Thank you.